have a look at motor drives. In 1999, we built this little thing here. A robot. When the robot wars first came on the screen, we decided to have a go at making something. But the problem is with a two-channel radio control, you've got forward and back, and just got left and right. It's not right lot of use for a robot which doesn't have a left and right steering. It just has a left and right motor. So I decided that you needed to adjust that to control it. So then I decided to build a little motor drive circuit using a new microchip that had come out, which is this one. In there's a complete microcomputer. So that's what's inside that chip. There's program memory there, random access memory there, permanent memory there. And then down here you've got your inputs and outputs. On this particular 18-pin chip, you've got 5 RA ports, 0 to 4, there, 0 to 3 and 4's there. And you've got 7 RB ports, 0 to 7, which you can define as GPIOs. And you've got all the other stuff that you need for it to be a complete microcomputer. So this is the circuit I'm going to use, which is actually this device here for driving motors. It's the same chip. There's one in that little box there, which intercepts the servo commands from the remote control, these servo positions, and works out how to drive the two motors. Yes. But nowadays we're on to computers driving servos, as you can see here. This little box converts serial into 8 servo signals. And I've got this application there that will drive it. So that's that little one. Oops. That one is on there. And then I've got 2 more, the last 2, going into this device, which will again convert the servo signals into a motor signal. So there I have the circuit that I'm using. There's the microchip in the middle. I've got a left and a right signal coming in, or in this case a single channel coming in. And there's a second channel going in for the second motor. Goes into those pins there. And then it produces 4 outputs, which are these signals here, into this H drive circuit. Which is this device. So the heart of that chip is actually these 4 transistors here. This particular chip, which has got this heatsink on, is bolted to the heatsink, will drive 4 amps on each channel. There's 4 channels, at up to 46 volts. So it's quite a powerful little chip. The smallest versions, which will drive, are 1 amp chips. And if you don't put the heatsink on, you can reduce its current as well. But the quite high voltage, some of these. So the heart of it is that you put your motor across the output there, and then the power go via the transistor through the motor, and if you turn one of the other transistors on the other side, it can go to 0. And then you've got the logic to operate there, that transistor, on that side, that transistor. And they're inverted, so a 1 and a 0. As long as you don't put both ones on one side, you're okay. And on this particular chip, it's got an enable as well, so you can disable all the ins and outs and the sensor, but we're not using any of that. So that's what the aim is, just to make this computer convert from the servo signal to a motor drive signal, 4 inputs and 2 motor outputs. Right, the next thing is we need to know what the servo signal looks like. Right, this little silver box here is even older. So this was built in about 1999. And this box was actually built for a BBC Model B computer. So it's a lot older still. It's connected via a serial port, so you can control it remotely via a serial link. Originally it was built as a data analyzer for a BBC computer or a 6502 processor. You could connect it across the microprocessor 6502 as was in the BBC, and it would remember where it went. But you could trigger it when it hit a particular address, and it would then remember where it went. And then as time went on, it got bigger memories added as the memories became cheaper. And then eventually there's some high-speed analog to digital converters came out. And they would do a conversion, an 8-bit conversion in 1 microsecond, which is quite fast for those days. As I say, we're talking about BBC Model B days. So I decided to put some of those in, so that it would now become an analog data analyzer, which is what I'm going to use it here for. Right, so I need to just set it up. So it's seen it. So I want it analog. Right. To save time, you can just dump a file on it and then we'll set it up for you.
The screen cap is not.
Oh, it's so great. Right. Oh. No, it's not working. It's not quite working. That's it. Right. So at the moment, it's the analog signal is connected across the output of this device here, or across the input to this device, which is actually the pulse generated as if it was a servo from this little box. So on the screen, they're all set in the centre, which is normally the off position. So that is the pulse you get out when the servo or the radio control is set in the middle. When it was running on a BBC computer, this black screen is what you would see on the screen of a BBC. It would draw the graphs, and that's virtually the same screen you would get. Right, I want to move it. The yellow is the trigger point. Because it's computer memory that it's storing it in, it's permanently running. when you get a tree of rent, it will then continue running for a set amount of blocks. That means you can actually see what happened before the trigger. So you can go backwards. There's nothing happening before the trigger in this case, but... So I've moved it now so that the trigger point is the first point. And I'm going to save that trace. So that's when it's in the centre. Right. So if I move that to minimum, and rerun it, that's what it looks like. That's what the trace looks like. Save that one. I'll put it on maximum. And rerun it. It's gone off the screen, which is why I've had to move it. So that it will just fit on the screen if I put it on there. Save that. So that's the maximum. Got another little program that I can display all the three together, centre, and maximum. In fact, I can make that a bit bigger. So you can see that when it's on the minimum, you've got a high pulse to signal that the servo is starting. Then you've got a period where you've actually got the amount the servo's got to move backwards. So that's when it's in the centre. So that's 0 position, that's maximum backwards. And then when it's over here, that's maximum forwards position. If you were driving it from one of these. So that's what I've got to decode with this microprocessor. I've got to work out these values. So we're going to write the program now to put in this microprocessor chip. So it's just a text file to start with. These are comments. The important thing is this line here, which tells the assembler that I'm going to use the that chip. These are to remind me how to set it up when I program it. I'm now going to define names because it's easy to put names in the numbers. So the TMR register is actually a number 1 and so on. So it's easier to put PCs and status. So this is just defining names to numbers. There's not that many addresses in this thing, so I have to change banks now and again. So bank 0 uses the same register as bank 1, but in bank 1 it's different options, different things it does. So you have to change banks now and again because it's quite a small machine. Again, I'm defining names to numbers. The carry flag and 0 flags, and another one I'm going to use later on. So I'm now actually going to define the things I'm going to use. So there's some spare pins here, so I'm going to use those to change the direction rather than having to change the wires, I can use those to change the direction of things. So if it's going backwards and I want to go forwards, I can put the link in the direction one and it'll do it automatically. It's a spare pin that I'm not using. The left channel input, the right channel input. The left is there, and the right is there. And I'm going to put an LED on it. There's a little LED down there, not this one for the power for that. There's a little one down there that I'm going to use for testing. But I can turn that on and off with a spare pin there. So those are all the RA register ports defined to numbers. And then there are RBs are the outputs, or mainly outputs. So got left front and left back for the top two, right front and right back for those two. And I've got some more spare pins that I'm going to use to tell it whether it's a motor or a relay, which is because in the old days we didn't have a H drive, so I had to have relays. In this little box there's relays to make it go reverse, because we didn't have H drives in 1990, whenever it was. And then there's two enables defined there. So now I'm going to define some variables. There's only one register in this chip, which is W. F is actually means you put it to its memory. So W is transferring into the register that it uses. To transfer things in and out of the CPU. Which is there, there's the W register. Everything else is classed as F, or a memory, or a random access memory, or a port. The only thing I haven't said on there is there's a crystal, 4 MHz. It's actually a resonator to drive it. Right, so that's defined. W is 0 and F is 1. I'm going to define some delays that I'm going to use. So I need to work out, I need to make it delay the processor for this period here. So that count, the delay is defined as 110. And there's a gap delay defined as 38. These are just, again, 110 is called left count. And then there's an output time, which is the one that's going to drive the motors. The next thing are the RAM locations that I'm going to use, which are these numbers, and I'm going to define those with labels. And now we're actually ready to start the program. When it powers up, it goes to address 0, so that's defining address 0. And it's actually going to go to setup, which is here. It's going to jump to setup, because address 4 is where it goes when it gets an interrupt. I'm not going to use interrupt here, so it's going to return from interrupt, because I'm not using it. So we're powered up, it's going to go straight into setup. Because of its limited number of registers, the first thing I've got to do is change it to bank, which is what that is. That sets the status RB0 part of the status register, which means it goes to bank 1. And now I'm going to define whether the pins are ins or outs with this TRISC A register. So RA0 to 3 are in, which are these. And 4 is the LED output there. So RA4 is an out. So that number, it's move literal, which means that number goes into W. So it's move literal into W, and then move W to F. and F is a register. Which there's a direction in this case of port A. We'll do the same with port B. RA 4 and 5 are in, the rest are out. So that defines that. And I'm going to use a timer to get, because I want to do a pulse width modulation to drive the motors, so I need a timer function. So that's the option register. So we look at the option register. So the end result is this timer register here, which you can set to count from various sources, depending on how you set it up. So this will count down, and when it hits 0, it will produce an overflow, and you can detect that. You do things with it. You can load it with a number, and it can count down. So you can drive that from various sources. That it's a pre-scaler, so you can pre-divide it by some number, or you can have it go into an external input. That will invert the input, just an exclusive OR gate, so it will invert the input, or you can have it from the internal oscillator. So I've got it set here. Bit 5 is 0, and the rest of them are 1. So bit 5, which is the TOSC, which is this one, is 0, so I'm driving it from the internal clock. And the rest is a 1, so that's a 1. So that's now set up. This time I will run from the internal oscillator. It's actually a 4 meg resonator, but it takes 4 cycles to do something, so it's actually only running at 1 megahertz. Is the internal chip itself is running at 1 megahertz. So that's the timer setup. I finished with the extra command, so I'm going to change it to bank 0. So it's a C, clear the status bit. It puts it back in bank 0. And now I want to turn the LED on. Mainly to say that it's powered up and going. The LED is from the plus supply, so I have to make it go to 0. So I clear it. So I'm now going to clear all the other stuff. I'll clear the port B, so all of these want to be 0. And I'm going to clear all the memory location, RAM locations I'm going to use, apart from the last one, which is, I'm going to put 255 in it, in fact, into it. Because this is my timer that I'm going to use for the pulse width. I'm going to clear the flag, the timer flag. So we're now ready to start doing something. We'll set everything up in the chip. Right, so now I need to look to see if the left channel has gone to 1 yet. So I'm looking at this pin here. So I'm looking at whether it's gone high. This command is branch if the result is set, which actually means it skips the next command if it's true, if the statement is true. So if the left has gone to 1, it skips the next channel, it skips the next instruction. So if it's 0, it goes on to somewhere else. So it's seen it going high, so it skips to this one. So it turns the LED on again, just in case. I'm now going to predefine the count I'm going to use, because I want to work out the time here. So I'm going to move literal into W, this number, which I predefined earlier, W to F, put it in the register, the count register. I'm going to predefine the left back as 127 and the left forward is 0, because I'm at this point here, or I will be. So that's maximum reverse. So I'm going to use the left back as maximum reverse, so I'm going to preload it with 127. I haven't got to the forward point, so forward is 0. So I'm now going to test to see if it's still at a 1. Skip if it's 1. I now want to count down, so I'll decrement that memory and skip if it's 0. That's what that command means. And because there's an F there, it puts it back in count. So it subtracts 1 from count and tests to see if it's 0. If it's 0, it skips. So it's going to go around that loop. It's going to go around that loop until it hits 0, which will delay me for this period over here that I'm not waiting for. So I'm actually ready to begin to work out where the number here. So I'm going to test to see if it's still 1, the left channel. If it is, I skip. No operation, it's just there to produce a timing delay. So I need 2 of them in this case. I'm going to decrement the left back, which I preloaded up there with 127. Put the result in F. And skip if it's 0. So I'm going to count down from 127 to 0 till I hit there. Going around that loop. So it goes back to the begin again. So go around that loop until that goes to 0. If it hasn't gone to 0, then we're in this section here. I'm turning the LED off in this case because I can use that to detect whether that number is the right number, which is how I did it. Is to monitor the state of the LED to see if the timer has expired yet, if I've got the right number in. Because in this case I've got it commented out because I can use it later to work out if these timings are right. Right. I want a bit of a gap here, around here, as a dead zone where the motors are not doing anything. So that's what this gap is. So I'm going to load the counter up with the number 38 and go around a little loop here to give me a delay, so I've got a bit of a dead zone around 0, so the motor's not running all the time, or trying to run all the time. And again, I can use the LED to signal whether I'm in the right place or not. So I'm now ready to go to this section over here. So I need to test whether it's still a 1. And now I'm going to increment the left forward value. It starts here and gets bigger. So I'm going to increment it but I want to know if it's got past 1 to 8. So this is branch if bit 7 is set of that number, that location. If it is, it means it's greater than 127. If it is, well, oh, right, yes, it's going to go around that loop now. Oops. It's going to go around that loop now, counting up. If it's got bigger than 127, I want to decrement it by 1, so it goes back down to 127. And now I need to wait and see if it's still high. I'm waiting for the ends because it's too big. The pulse is too big. So now, at this point, at the end here, right, so I'm turning the LED off anyway. And I've got a valid number now for the motor, so I can put the enable on, I can turn that on, and so I'm setting the enable there, which is that pin there. And now I can test the direction, which is direction 1. So if the link's in, I'm going to skip. If it's not in, then I'm going to go to the calculator. So all this is going to do is reverse the left and the right, the forward and the back numbers. So I'm now ready to calculate the speed of the motor. So I've got 2 new variables, the left forward position and the left back position. I'm going to clear those to start with. I'm going to move in the forward number, and I'm going to skip if it's not 0. If it's 0, I don't want to run the motor, so I want to go somewhere else. So the left forward is not 0. So I'm now going to store it in the left forward. I loaded the left forward. I'm going to store it in the left LF position, and I'm going to times it by 2. That rotates the 0 to 7 bits. So it's going to times it by 2 in effect. It's going to shift all the bits up by 1 bit. Now I'm going to go to the end. So if that was 0, I'm going to check whether the back was set. We'll do the same. Right, we're on to the next. The next is identical, but for the right channel, or for the second channel. So exactly the same set of commands. I'll go back to the beginning again. So test it to see whether it was high. If it wasn't, it went to next. Next is there. That tests the other channel. If that's not high, it goes to the output. Which is there. So we've gone to the output. Now I'm going to test the timer to see whether it's overflowed yet. If it hasn't, we'll go back to the main and look for a new input. So if the timer event happened, then I'm going to reset the timer and reload its number, and I'm going to increment the on time which I preset earlier. So, and that's going to skip if it's 0. 0 is the first time. If it's not 0, it'll go to that. So it's 0. The O time is 0. So I want to set the motors going. So first of all, I turn everything off, clear the motors, and I move the position, left front position, skip if it's not 0, And I'm going to go over there. If it's not 0, I want to turn the motor on. Now I'm going to the right output. I'm going to do the same with the back. And then I'm going to test the right signal. So that if that on time was 0, I want to set the motors running if they need to run. If the on time is not 0, and I'm going to go to this bit of program, which is here. I'm going to move the position. I'm going to test if it's 0. If it's not 0, I'm going to skip. I'm now going to subtract from the left from position from the O time to see if the numbers agree. So, and I'm going to skip if it's not 0. So if the numbers agree, I want to turn the motor off because I've counted up to that position. And I'm going to do the same with the back and the same with the right. So I'm now come to the end of the program. So that's it. That's all that's in the program. So I need to assemble it, convert it into binary. So we've got this little helpful guy. Created this program quite a long time ago now. My cook came here to one of his talks and it was about this. And it's been very useful to me. So if I drag that text file into there and assemble it, it will convert it into a binary file and another file with extra information for me, which also indicates if there's any errors in there. There's no errors, so that's worked fine. I also wrote a simulator. Drag the binary file into the simulator, it will load it in. So I can now run the simulation of that code that I've just written to see if it does what it's supposed to do. If we use this text file, which has got extra information in it, produced by the assembler. Go to where it starts there. It's actually put in the memory addresses, or the program addresses for me. So it's loading address 0, which is where it's going to start. And that immediately says we go to address 5, which is there. Text step, it's gone. And that says, as it says there, status flag, the status which is there, the status register. It's going to set bit 5, which is there, RP0 to 1. There. So set it to 1 and it changes it to bank. To bank 1. So I'm going to go through all this again. So we're up to 7, move that into the RA ports. This is going to change the direction of these inputs and output ports from this bottom row RA when I take the step. There it is. They're all in, apart from that RA4, which is the LED drive. That's the 0, download. Take another step, which has moved that 30 into the W register. and then it's going to change the directions of these bolts there. Option register, which is up there, it's going to define the register in there, which is there, change that to 0. And now I'm going to change the bank back, so that point now will go to 0. And then I'm going to turn the LED on. It's actually already on. Oh no, there it is. It's gone to the black, so it's gone to 0, so that's turn the LED on. And now I'm going to clear the bit port B. So that's all turned off. Now I'm going to clear all the RAMs, we're going to use the RAM addresses. So the RAM address there is 10, which is this point here, so that all these will go to 0 as I run through them. Right, this last one will load 255 into the W. To the W register and put it in. Load time is 18, memory location 18, which is that one there. I'm going to clear the timer flag, which is inked on register, and it's TOIF, which is this one. It's already clear. So now, at this point, address run here. So I'm now going to test the input channel. It's 0, but I put it down to 0. So it's going to jump round to the next location. It's going to test the other port, and that's also 0, so we'll skip it. It will go to the output, the watch code, which is address 80, as it says. There, so I'm going to address 80. It's going to test the timer flag, which is up there. Going to go back to the beginning again. So it's going to go around that loop until something happens. So if I make that high, so we've now got an input, you'll see it skip this time. Oh, well, we haven't gone to that. It's gone to what address running now. Now it's going to test it. This time it will just skip. Rather than go to the next, it will skip to 1C. Turn the LED on. It's already on. We preload the count. So 60 now in binary, 110, binary 60 hexadecimal. We'll put that into W, and then it will move it to the location D, which is there. Gone to that. 127 into that. 7 into address 11, which is there. And we can clear out the forward, which I like that anyway. So now we're at 22. Just 22. Test the port, see if it's still working, it is, so I'm going to skip. So I'm going to decrement the timer now. And the timer is F. So this number is going to go small, decremented. So I'm going to go around this loop here, decrement it, and go around it and test it until that hits 0. Right. You set breakpoints here, so when it's gone round that loop, it's going to come out to address 26. So go in there, put in 26. If I run it this time, it will stop when it gets to 26. So that's counting down. Right. When it hits 0, it's got to address 26. So we're now at address 26. Turn the LED off. So I'm now ready to go around this loop, counting down the back. So if I put in address 2D, you'll see that that number there will count down because it still high as the input pulse. Put address 2D in there and run it. And that number will count down. Just stop that. Speed set. Right for that. Super there. So I've now got the gap. Go around the gap. And again, I want to end up at address 31. I'll put the number in there that's going to count down with. I want to stop it when it gets to address 31. It's not a very big number, so what I'll do with that. So we're now at address 31. I'm now going to go around this specific program and count up this time. I'm incrementing that address, that RAM location 10 as I go around the loop. I want to put another breakpoint in now to stop it. So it's 37. Change that to 37. And run that. So I'll go around there until... Oops, do something like that. It's gone too far. It's gone too far from it anyway. I'll skip on to the output event. I'm putting the address here at 18. Depending on this timer, it's there. It'll stop when the timer's gone through 0. We're at address 18. I'm going to reload the timer with its new value. It's gone there. Right, I'm going to cheat and fill in the O time value, which is 18. So you can see what happens when it's 0. I missed it. Run that again. I want, or to the divide, because I want it to be 0 when I come round again. So round again, now 8D, reload the timer, increment 18, so it was FF, increment it, and skip it at 0, it is 0, so I want to go through this bit of program, so we're at 91, we're at address 91, which is there, so turn the motor off, see if there's anything in that left front. There is. So this time I want to turn this motor on, so this goes here. Yeah, it's come on. Because there was a number in there, it's turned that motor on. I rerun that. This time, when it comes round, it's not 0. So we'll go to that address there. Oops. So we're here, that's it. It's going to go to A6. So it's now going to test to see if it should turn it off. Test to see if it's 0 now. It's going to subtract that value 1, which is the O time from the position. And the result's gone back into the Z flag is 0, not 0. So it's not going to turn the motor off this time. It's going to do the same with the other channel. It's going to go right round again until it hits the number. So I know the number's 1C, so we preload that way 1B. Take them round again. Down to 1C, so up to A6, move it there, subtract to the value of the 18, so this time W has gone to 0, the result's 0, because it's equal. Z flag's gone to 1, so skip it's not here. It is equal, so this time I'm going to turn the motor off, so that pin there will go to 0 on the next step. There. So I've now turned the motor off when that number's hit. So the program looks like it's going to work. Right, the next thing is we need to get it in the chip. So there's also written a blower. Might look. It connects to the printer port of this PC, that's the box there, for the programmer. So, it's a crystal oscillator. It's actually a resonator, but it's the same thing. So I need to set that to crystal. And also, it's a newer type, it's F84, not C84. So I need to set that to 1, which is that. I need to tick that. So I'll put that in there. Drag the file onto it, and blow it. Yeah, it's done it. No, it's quite a small program. So the program is now in there. Right. I actually need to put it in there and see if it does what it's supposed to do. Set up this up to 3 channels. And rerun it. Isn't far enough. Help if I put it in the right place. Right, so I'm now monitoring with the second channel, monitoring the state of the LED output. So in the program I turned it off after the initial start pulse. So if I put that to minimum, rerun it. This should just about line up, so I know my timing is right. So that's the gap. The third channel is actually on the other servo channel, so step along a bit. You see that the other channel is there. And if I look at the program for the other channel, so I've got the LED being turned off. So it's been turned on when the first high pulse comes along, and it's been turned off after the first gap, first bit of testing on the left channel. On the right channel, it's turned on again when the right goes high. It's commented out on the first one, and it now gets turned out there at the beginning of the gap. So you can see that it's there, it's gone high there, it's been turned off there. So that's where the gap starts, the dead zone starts. So I can then change the program, move these markers on to get the right numbers, and that's how I've got the numbers in the program. Basically. Trial and error by seeing what happens, making a guess, and then changing these numbers till I get the right value.
So there's no sort of formula, it's all try it, suck it and see.
It's all, yes it is. So if I actually connect some power to this motor, drive circuit, it actually runs there. It's in the centre, nothing happens. I've only got one motor, unfortunately. So that's full reverse. You can probably hear it slow down. Yeah, stop. And it'll go the other way, start to go the other way. And get faster and faster as the numbers increase. So that seems to be working. So that's how to program a motor drive circuit. Right, I think that's all I've got to say on it now. Over on Terry's little robot, there's one of these motor drives. Driving these motors. So that's how I created it, and that's the actual use over there. So with a bit of luck, we should be able to get that working. There's a Raspberry Pi sat on there. There's one of these little boxes, it's not as big as this is quite an old one. There's one of these which takes the serial signal, converts it into 8 servo signals. Then you've got your 2 into the motor drive, and it's also got 2 servos driving the infrared detector on the front of it that you can see. Right, so we'll see if we can get that working now.
Yeah.
Rock, helping you with Acorn and Riscos computing.